Welcome! Today, we're going to get into the hidden engineering that really powers our world. We're talking about the fundamental mechanics of motion. You know, the stuff that lets machines actually do their work.
So, have you ever really stopped to think about how complex machines actually work? I mean, everything from a giant industrial loom down to a simple sewing machine. How do they work so flawlessly? Well, at the very heart of it all is this one huge engineering challenge. How do you make them start exactly when you want, stop safely every single time, and, ideally, do it all without wasting a ton of energy?
All right, let's dive right in. The very first problem seems simple, but it's crucial. Just getting the power from the motor to the parts of the machine that do the actual work. How do you transfer that force effectively?
To solve that, engineers basically came up with two classic solutions, which you can see right here. You've got the flexible belt drive, which, you guessed it, uses a belt to connect an external motor. And then you have the direct drive, which is way more precise because the motor is built right onto the machine's drive shaft. The key difference is that connection. One's indirect and flexible, the other is immediate and totally rigid.
And that difference? It's not just theoretical, it's something you can actually feel. I love this quote from a leatherworker. He says, a direct drive system gives a very positive feel and solid response. And why is that? Well, it's because there's pretty much zero slack or delay. The link between the power and the action is instantaneous.
But of course, like with pretty much everything in engineering, it's a trade-off. Direct drives are awesome for that super quick response, and they vibrate less. But that tight integration has a downside. Because the motors are often proprietary and you've got more electronics in the mix, repairs can get a lot more complicated and, frankly, more expensive.
Okay, so getting a machine moving is one thing, but making it stop is just as important, maybe even more so. I mean, how do you control all that momentum reliably and, most importantly, safely?
To crack this problem, engineers turned to three fundamental forces, each with its own special properties: the simple pressure of compressed air, the incredible power of pressurized fluid, and the invisible but surprisingly strong pull of magnetism.
And these three forces, well, they're the foundation for the three main types of industrial brakes. These are the systems that keep our world running and, stopping smoothly and safety.
And this table here really lays it all out. It's all about picking the right tool for the right job. If you look at braking force, you'll see pneumatic and hydraulic systems are rated high. They're the heavy hitters, perfect for things like giant cranes. But for lighter machines where response time is everything, that's where electromagnetic brakes shine. They're fast with low maintenance, making them the perfect choice.
So, we've figured out how to go and how to stop. But for decades, both of these have been haunted by this invisible enemy. It's a fundamental flaw that wastes just a staggering amount of power. And it's something modern engineering is completely obsessed with solving now.
And that enemy, it's simply wasted energy. See, the traditional brakes we've been talking about are friction brakes. They work by taking all that incredibly useful kinetic energy, the energy of motion, and turning it into something totally useless that just radiates away: heat. Every single time a machine stops, all that power is just gone, thrown away.
And believe me, we are not talking about a little bit of waste. To really put this into perspective, the surface of a normal car's disc brake can hit a mind-boggling 1,000 degrees Fahrenheit when you slam on the brakes. That is pure energy transformed into heat and just vanishing into thin air.
So how in the world do we fix this massive energy leak? Well, the answer is this incredibly elegant solution that's already changing everything, from Formula One cars all the way to the wearable tech you might have on your wrist.
It's called a kinetic energy recovery system, or KERS for short. Now, instead of just turning motion into wasted heat, KERS acts like a piggy bank for momentum. It literally captures that kinetic energy when you brake and converts it back into usable electricity that you can store in a battery. It's a total paradigm shift. We're going from just getting rid of power to actively recapturing it.
And look, this isn't just some sci-fi tech for race cars anymore. The technology is scaling down to the machines we use every day. This concept, for example, it shows how the braking motion of a simple sewing machine can actually be used to drive a little generator. It recaptures its own energy to be stored and used again. Basically, the machine is starting to power itself.
This is really paving the way for a whole new generation of self-sustaining, ultra-efficient devices, everywhere from our factories to our homes. And that leaves us with one last, pretty provocative thought to chew on. What happens next when our machines don't just consume power, but actually generate it too?